Hello everyone. In today's lecture we'll move to the new chapter, which is the time domain representation of LTI systems. In the previous chapter we've learned about the different types of signals and their classifications, and we have seen the basic operations performed on signals like time shifting, mirroring, and scaling, and we've also discussed the systems and their properties like stability, causality, linearity, and time variance, and so on. In this new chapter we have today, we will focus on a category of systems which satisfy the linearity property and time invariance, the LTI systems, the linear time invariant systems. And we will try in this chapter to focus on the representation of this kind of systems in time domain. So how the input and output of this kind of systems are related and how to compute the output in terms of the input. In the next chapter, we will talk about LTI systems but in a different domain that's called the S domain or the Laplace domain. So the objective here is to examine the different methods of describing the relationship between the input and the output of a linear time invariant system in time domains. The objective of this chapter is to describe the relation between the input signal and output signal of an LTI system in time domain. Both input and output are considered as functions of time. Of course, methods for relating the system output and input in different domains other than time are developed in later chapters, which is basically the Laplace domain and the S domain. Okay, why we are actually trying to represent the systems in time domain? For two reasons. First, for analyzing and predicting the behavior of LTI system. If you design an LTI system and you apply a certain input, you need a way to describe the relation between the output and the input. What kind of input will generate what kind of output, and so on. And this will help us in implementing systems and especially discrete time systems. We have actually four methods of representing the LTI systems of describing the relation between the output and input. The first method is the impulse response, and this will be the focus of this chapter. We mainly in this chapter will focus on the impulse response and what is it actually and how can we use it to describe the relation between the output and input. The second method is using differential equations or difference equations, where the LTI system is characterized by differential equations or difference equations, and then we can describe the system using this equation. As a matter of fact, in the next chapter in the Laplace transform, we will see how we can use a differential equation to describe a system and how we can transform it into an impulse response and move on. The third method is using block diagram representation, where a system can be represented using mainly three elementary operations: multiplication, addition, and shifting. But again, we will not deal with this kind of representation right now. It's kind of out of scope. And the fourth method is a state variable description. Again, in this chapter, we will mainly focus on the first method, which is the impulse response of an LTI system. All four representations are equivalent in the sense that identical outputs result from a given input. So if you choose to represent your system using any of these four methods, you will get the same result. They are equivalent to each other. But different representations give different views of the system, which will give different insights on the system's behavior and how does the system operate. So let's move on to talk about the impulse response, which is the main focus of this chapter, and see what actually is the impulse response. The impulse response of an LTI system is defined as the output of the system due to a unit impulse applied at time t equals 0 applied at the input. The impulse response basically it completely characterizes the behavior of the system. In order to understand this definition, let's move to our whiteboard over here. So let's say we have an LTI system, a system that's linear and time invariant. And this system has an input x of t and the output is y of t. So what is the impulse response? The impulse response is basically the response or the output that will be generated from this system if this input is equal to an impulse. In other words, if we set x of t to be equal to delta of t, an impulse located at 0, in this case the output y of t will be equal to the impulse response, which we call h of t. So again, the impulse response h of t is the output that will come out of the system if the input is made equal to an impulse delta of t. So let's read the definition one more time. The impulse response of an LTI system is defined as the output of the system due to a unit impulse signal applied at time t equals 0 or n equals 0. It also goes the same for the discrete time system. So applying an impulse delta of t or delta of n for discrete time systems at time 0 will result in an output. This output is called the impulse response, and as the name implies, it's a response of the system due to an impulse. How can we obtain the impulse response of a system? First, if we know the system configuration and dynamics, then we can get the impulse response. And there are many examples in mechanics and in circuits where if you know how the system works, you can get the impulse response. But for unknown systems, if there is a system that you do not know, you can measure the impulse response by applying an approximate impulse, because the impulse delta of t is a kind of a theoretical function where the width is 0 and the height is infinity. You cannot actually generate this kind of function in the lab, but you can have an approximate impulse, a pulse that's very narrow and has very high amplitude. Apply this kind of pulse on a system and measure the output. The output will be kind of the impulse response. For discrete time systems, it's easy because delta of n just a value of 1 at instant 0, but for continuous time systems, you cannot have an actual impulse, but you can have an approximate impulse, and then you can get the impulse response. Given the impulse response of an LTI system, we can determine the output due to an arbitrary input signal. How's that? By expressing the input signal as a weighted superposition of a time-shifted impulses. This statement is kind of confusing. We will discuss it in details in a few minutes from now. But again, for an LTI system, if you know the impulse response, you can find the output for an arbitrary input, for any input. And forget about these two lines. We will discuss them in details in a few minutes from now. And basically, this will result in the so-called convolution sum or convolution integral. We will talk about this in a few minutes from now. Okay, so the convolution sum. In order to understand this part, we need to understand that any discrete time sequence x of n can be represented as a weighted sum of time-shifted impulses. We will start with the discrete time case because it's simpler, easier to understand, and then we will do the continuous time thing. So any discrete time signal x of n can be represented as weighted sum of time-shifted impulses. We have discussed this before, but let's try to say it one more time. So the equation here is saying that x of n in a discrete time signal can be represented as a summation of delta of n minus k, which is a shifted impulses in the time domain, weighted with a constant x of k. And we have seen this in previous lectures, but in order to understand it or to repeat it, let's go back to our whiteboard over here. So imagine we have this kind of function x of n, and this x of n over here has a sample of value 2 at instant minus 1, and 1 at 0, and 1 at 1, and half at 2, and so on. So this signal can be represented as 2 times an impulse delta of n plus 1. This impulse, delta of n plus 1, is actually happening at instant n equals to minus 1, and it's weighted by the constant 2. And here we have an impulse at 0, so we have 1 times delta of n. So the impulse at 0 and the weight is 1. We have impulse at 1 with weight of 1, so delta of n minus 1. And this sample at 2 would be 1/2 delta of n minus 2, and this would be delta of n minus 3, and so on. So any discrete time signal x of n can be represented as summation of shifted weighted impulses. Impulses that are shifted in time, delta n minus 1, delta n plus 1, and each impulse would have the weight, and this weight basically is the function at this instant. So if you take a look at this impulse, delta of n plus 1, this 2 is actually the weight of the function at instant minus 1. It's basically x of 2. This is basically x of 2. So going back to our slides, here we have x of k times delta of n minus k. Any discrete time signal can be represented in this form. Shifted impulses, and each impulse would have a weight of xk. So let's say we have an LTI system whose operator is h, and we need to apply an input x of n and find the output signal y of n. And applying x of n as the input to the system h, the output y of n can be computed as follows. It's h acting on x of n, or h acting on the summation of x of k delta n minus k. But as we have seen in the linearity property, the linear system acting on summation of elements is equivalent to the system H acting on each individual component and then adding the result. So basically we can exchange the summation and the operator H. So we can move the summation outside and H inside, and now we have summation H of x of k times delta of n minus k. And now, since n is the time, so delta of n minus k is a function of time, but x of k is considered to be a constant with respect to time. So we can move it out of the operator h, which will give us summation x of k times h of delta of n minus k, which is basically the system h acting on a shifted impulse. But since the system is time invariant, applying the system on a shifted impulse will result in a shifted impulse response, h of n minus k. So applying a shifted impulse to the system will give us a shifted impulse response. So now the summation would be summation of x of k times h of n minus k, going from minus infinity to plus infinity. And this is actually the convolution sum. And here the output is a weighted sum of time shifted impulse responses. So we have h of n, and then it's shifted in time, h of n minus k, and then it's multiplied by a weight or a constant x of k, because it's constant with respect to time. This definition actually is a convolution sum. And let me try to do this derivation one more time in a simpler notation. So let's move to our whiteboard over here and see how it goes. So since we have an LTI system, a linear time invariant system, we can do the following. If we have an impulse delta of n applied to the system h, the output will be an impulse response h of n. And since the system is time invariant, a shifted impulse delta of n minus k applied to the system will give us a shifted impulse response, h of n minus k. And since the system is linear, multiplying delta of n minus k by a constant like x of k applying it to the system, we will get the same constant x of k multiplied by the shifted impulse response h of n minus k. And here one might ask, how can we say x of k is a constant? It's constant with respect to the time n, because the time is n. Delta of n minus k is function of time, but x of k is constant with respect to time. That's why using the linearity property you can multiply by a constant at the input and the output will be multiplied by the same constant. This was called the homogeneity property. And then the linearity will also allow us to sum these components together, and the output will also be summed together, because in linearity, if we have the superposition property which allows us to add the corresponding output coming from for a certain input. So now summation of x of k times delta of n minus k is actually the input x of k, x of n. As we have seen here, any signal x of n can be represented as a summation of xk times delta of n minus k. So here we have a summation xk delta n minus k. So this is basically the input signal x of n. And here we have summation of xk times h of n minus k, which is the convolution sum we have here in this slide. Summation of xk times hn minus k. So this is a common question in the exam to ask you to prove the convolution sum. Show that the output of an LTI system is actually the convolution of the input and the impulse response. So this summation is referred to as the convolution sum, and we use this symbol to represent the convolution operation. So to wrap things up, if we have an LTI system whose impulse response is h of n and whose input is x of n, then the output y of n can be computed as the convolution between x of n and h of n. Again, this symbol is not multiplication, it is convolution. And the convolution is defined by this summation from k to minus infinity to plus infinity x of k h of n minus k. If you take a look at this summation, n is the time and k is a dummy variable, because when you do the summation over k, k will kind of disappear and the resulting function will be function of n time, y of n. So it can be easily shown that the summation x of k times h of n minus k is equivalent to the summation of h of k times x of n minus k. And these are the two definitions of the convolution sum. So in order to understand this equation and how can we implement it, let's move to our whiteboard. And remember that we want to do the convolution of x of n and h of n. X of n is the input to the discrete time system, and h of n is the impulse response of the discrete time system. Moving here, so we have x of n and h of n. In order to do the convolution, we go as follows. First, we replace n, the variable for the time, with another dummy variable. Give it any name, k or l or m, it's fine. So let's use k, so x of k and h of k. So the first step in doing the convolution is to replace the time n with a dummy variable k. The second step, we will choose one of these two signals to keep it as is, and the other one we will do a mirror, then a shift. So I will choose to keep x of k as is, and h will first be h of minus k, so we'll do a mirror, then shift by n, so h of n minus k, and then we can multiply x of k times h of n minus k under the summation, and this will give us the convolution sum. Let's go back to our slide. Here we have x of k times h of n minus k under the summation. Here x of k times h of n minus k. So again, first step, replace n by k. Second step, choose one signal to keep it as is, in this case x of k, and the other signal we will do first a mirror, then a shift. Then we multiply x of k times h of n minus k. Or equivalently, we can keep h of k as is and do a mirror on x, so x of minus k, and then shift x of n minus k, and then we multiply h of k with x of n minus k under the summation. And this will be actually the second definition here, h of k times x of n minus k under the summation. These are the two definitions of the convolution sum. And the convolution basically computes the output of an LTI system y of n by convolving the input x of n with the impulse response h of n. The convolution operation for discrete time systems is illustrated in the next figure. We're gonna take a look at it, where the input signal is decomposed as the sum of weighted and time shifted unit impulses. As we have seen before, any input signal x of n can be decomposed as a summation of shifted impulses multiplied by a constant x of k. And in this case, due to the linearity, the corresponding output would be shifted impulse response h of n minus k times the same constant x of k, and then we will add them together. And total output is the sum of those outputs. So if this is x of n and we're applying it to an LTI system whose impulse response is like this, and we want to find the output. So let's look at this figure and see how it goes. The input we have, first we have an impulse at n equals to -1, and this impulse has a weight of -1. So this impulse will result in this impulse response, but shifted in time. Instead of starting at 0, it should start at -1, and it will be multiplied by a constant, this weight, this -1. So this impulse response will basically be shifted, which will start at -1 and will be scaled by a factor of -1. And this should be added to, here we have an impulse at 0 and its weight is 1/2. So this impulse will result in this impulse response weighted by half. So the same impulse response weighted by half. And then at k equals 1, we have an impulse with weight of 1. So this will result in a shifted impulse response. This impulse response will be shifted to the right by step 1, and it will be scaled by a factor of 1, giving us this impulse response starting at 1. Same here. So, and if we add all these together, we will get the output we want. Example: consider a discrete time system, LTI system, who has the following relation: y of n equals x of n plus 1/2 x of n minus 1. First, we need to find the impulse response of this system, and next we need to get the output for this input, x of n. So let's see how it goes. So let's move to our whiteboard over here. And here we have a system who is described by the relation y of n equals x of n plus 1/2 x of n minus 1. And the first part of the question is asking us to find the impulse response. In order to find the impulse response, we need to apply an impulse. So we will let x of n to be equal to an impulse delta of n. And in this case, the output y of n will be called the impulse response, h of n. Again, the impulse response is the output of the system when the input is an impulse. So in this case, replacing x of n with an impulse, we will get delta of n. And this term, x of n minus 1, will be delta of n minus 1. So plus 1/2 delta of n minus 1. And if we try to plot this, so we have an impulse at 0 with the weight of 1, another impulse at 1 with the weight of half. It's 1 delta of t plus 1/2 delta of n minus 1. Delta of n, 1/2 delta of n minus 1. So this is the impulse response we have, h of n, and this is the first part of the question. The second part, we need to determine the output of this system in response to the input signal described as follows: an impulse with the weight of 2 at time 0, another impulse with the weight of 4 at time 1, an impulse with the weight of minus 2 at time 2. That is, x of n can be described as 2 delta of n plus 4 delta of n minus 1 minus 2 delta of n minus 2. So, how can we compute the output in this case? So, this delta of n, this impulse, would generate an impulse response, h of n, and it will be weighted with this factor 2. So, basically, the output in this case would be 2 times h of n plus this shifted impulse delta of n minus 1 will give us a shifted impulse response h of n minus 1 because the system is time invariant. So we'll have 4 times h of n minus 1. And this impulse delta of n minus 2 will give us shifted impulse response. Again, it will be minus 2h of n minus 2. Now, what allowed us actually to separate or deal with each impulse separately and generate the output corresponding to each impulse separately and then add them? It is the linearity. If you remember from the previous chapter, a linear system would allow us to deal with each component of the input individually and add the corresponding outputs. So now y of n is actually 2h of n plus 4h of n minus 1 minus 2h of n minus 2. And if you take a closer look at this expression, this is actually the convolution sum. So let's see how is that. So using the convolution sum, y of n is equal to summation of x of k times h of n minus k, for k going from minus infinity to plus infinity. But in our case here, the signal x of n is only extending from 0 up to 2. So the summation here would be going from 0 up to 2, which will be x of 0 times h of n plus x of 1 times h of n minus 1 plus x of 2 times h of n minus 2. So again, this example will help us to understand the concept of convolution and how that this equation is simply saying that using the properties of linearity and time invariance, we can separate the input into summation of shifted impulses, and each impulse will give us a shifted impulse response weighted with the constants x of k, x of 0, x of 1, x of 2, and so on. So the first step is easy here. We found the impulse response, and now that we have x of n as 2 delta of n plus 4 delta n minus 1 minus 2 delta n minus 2, now using the linearity and time invariance we will get y of n as 2h of n plus 4h of n minus 1 plus minus 2h of n minus 2, and h of n we already know h of n to be delta of n plus 1/2 delta n minus 1. So if you try to do the math, you will get this kind of result, which is n equals x of n, y of n equals 0 for n less than 0, equals 2 for n equals 0, and so on. So this is basically h of n and h of n minus 1, h of n minus 2, then you have to add, then using the weights you have. This approach used here is effective only if the input is of brief duration. The input here had only 3 samples, and the impulse response only had 2 samples. But when the input is of long duration and the impulse response as well is of long duration, the approach becomes cumbersome. Now we need an alternate approach to do the convolution, which is basically this equation, and the approach is simply what we have already described over here, where you replace the variable n with a dummy variable k and choose one signal to keep it as is, and the other one is to mirror and shift and then multiply them together. And we're going to do that actually in a graphical approach. Okay, so convolution sum evaluation procedure. How can we evaluate this convolution sum? Okay, please note that in the right hand side of the convolution sum, this equation, the right hand side over here, k is the variable where n is a constant. If you look at this expression, k is the variable over which we're doing the summation, and n is a kind of constant over here. Okay, so first step, we replace n with k. So if you want to do the convolution of x of n and h of n, first step we replace n by k. Same for h. h of n will become h of k. Then we will choose one signal to keep it as is. In this case, x of k will keep it as is, and h of k, we will change it first to h of minus k, which is time reversal, which we have studied in the previous chapter, followed by a time shift, it's h of n minus k, which also we have studied in the previous chapter. Now we can multiply x of k times h of n minus k and do the summation. Or equivalently, we can keep h of k as is and get x of n minus k, as we have discussed before. Okay, so if n is negative, we shift h of minus k to the left. If n is positive, we shift h of minus k to the right. We're going to see this in an example later on. We can choose to keep h of k as is while time reversing and shifting x of k to become x of n minus k. Example. Consider a system, a discrete time system, whose impulse response is 3 over 4 to the power n u of n. And we need to determine the output y of n when the input is u of n. Or equivalently, I can ask you to find the step response of the system. The step response of a system is the output that comes out of the system when the input applied is a unit step u of n. Before we continue with this example, we need to remember two summations that are actually very important, which we are going to use in this course a lot. The first summation is r to the power n as n goes from 0 to infinity. This summation is a summation of a geometric series, and it's equal to 1 over 1 minus r if modulus r is less than 1, and it goes to infinity if modulus r is larger than or equal to 1. If r, let's say, is equal to 1/2, this summation would be 1 plus 1/2 plus 1/4 plus 1 over 8 and so on. All the terms are kind of decaying. That's why the summation will converge to 1 over 1 minus r, which is half in this case. But if, let's say, r is equal to 2, we will have 1 plus 2 plus 4 plus 8. All the terms are growing up. That's why the summation will diverge and will go to infinity for any value of r whose modulus is larger than or equal to 1. The other summation that's very important, r to the power n also, but from 0 to n minus 1. This is up to infinity, but here it's up to n minus 1. And this summation will have two forms. If r is equal to 1, then we have r to the power 0 plus r, which is 1 plus 1 plus 1 plus 1. This will give us n terms. N times 1 is n. If r is not equal to 1, we will get this form 1 minus r to the power n over 1 minus r. And please note that this capital N over here is whatever appears in the upper limit of the summation plus 1. So if here we have 9, we will have 9 plus 1 will get here r to the power 10, and so on. So this n capital is basically whatever appears here on the top of the summation plus 1. Okay, so let's go back to our example. We have an LTI system with this kind of impulse response, with this input unit step, and we need to find the corresponding output. So let's move to our whiteboard over here, where we have x of k and h of k and x of k. And keep in mind that here, since the system is an LTI system, we need to do the convolution of h of n with x of n. Doing the convolution implies using the following steps. The first step is to replace the variable n with k. So instead of h of n, we will have h of k. And the second step, we will have x of k instead of x of n, which simply means we will draw h of k and x of k with respect to the variable k rather than n, just to replace n with a k. The second step, we will choose one signal to keep it as is, and the second signal, the other signal, will be mirrored and then shifted. Usually, we choose the signal that's simpler, that's easier to deal with, to do the mirror and shift, and the signal that's kind of more complicated, we will keep it as is. So I will choose to keep h as is, and I will choose to mirror and shift x of k. So if we will start by mirroring x of k, and mirroring means simply reflecting the signal. So whatever happens at 1 will happen at -1, and so on. So this would be the signal we have. This is x of minus k. And then we will do a shift. We will shift the signal such that instead of starting at 0, it will start at time instant n. And this is x of n minus k. And now we are ready to do the convolution. We will do it actually graphically. So before we go on in doing the convolution, first step, we'll change the variable n with k, h of k and x of k. We'll choose one signal, keep it as is. In this case, I will keep h of k as is. And x of k, I will do the mirror. So instead of having a unit step going to the right over here, it will be a unit step going to the left and starting at 0. And then we will do a shift. So instead of starting at 0, it will start at instant n. Now this is x of n minus k. Now we are ready to multiply h of k by x of n minus k and do the summation. So we have already found x of k and h of k and x of n minus k, and now we're ready to do the convolution. So let's move to our next slide over here. So we have, this is h of k and this is x of n minus k, and x of n minus k is a unit pulse, unit step starting at instant 0 and going to the left. Now n is a variable, and in this case over here we have n is less than 0. As we can see, this is the origin 0, and n here is less than 0. So if you multiply h of k and x of n minus k, you will get actually 0. How is that? All the samples here of h of k are equal to 0. We multiply it by these, so we will get a 0. And all the samples here are 0. We multiply it by 3 over 4 to the power k, which will give us a 0. That's why the multiplication will be 0 for n less than 0. So let's write this one down. So y of n would be equal to 0 if n is less than 0. Now let's move back over here. What would happen if n is larger than 0? So basically this n will be shifted right here to be larger than 0. Let me draw it one more time. So if we take a look at this case where n is larger than 0, this signal will be shifted to the right. So let's go back. Here n is less than 0, so the impulse, the unit step is starting at instant n, minus 1 or minus 2 or whatever, so the multiplication is 0. But as n increases, if n goes larger than 0, the first impulse will appear over here after the 0, as we can see in this slide. Here n is larger than 0, so we're starting, the unit step starts actually for n larger than 0, as we can see over here. Now if we multiply h of k and x of n minus k, we will get non-zero values. So for all the samples before n equals 0, before the time equals 0, all these samples will be multiplied by 0, and so it will be 0. And all the samples for k larger than n will also be multiplied by 0, hence it will be 0. The only non-zero values would be from k equals 0 up to k equal to n. Again, multiplying these two together, the only values that will remain will be from k equals 0 up to k equal to n. That's why we can write the summation like this. So if n is larger than or equal to 0, we will have the summation of going from k equals 0 up to n, and then we multiply h of k times x of n minus k. H of k is 3 over 4 to the power k, and x of n minus k is actually just 1 because it's a unit step. So now we have this kind of summation, and this kind of summation can be evaluated easily using the rules we have seen before. So now y of n is equal to this summation, k going from 0 up to n of 3 over 4 to the power k times u of n. Why do we have this u of n? If you go back over here, basically the y of n is 0 for n less than 0, and for n larger than or equal to 0, we have this expression, which is equivalent to multiplying this expression by u of n. U of n will kill any sample before 0, will keep any sample after 0. So let's go back over here and do the summation. And this summation is one of the two summations we have seen previously in the slides. Basically, it's this summation r to the power n going from 0 up to n minus 1. So this summation would be 1 minus 3 over 4, and here 1 minus 3 over 4, and then we'll take this n and add 1, so n plus 1, and this would be the output from this system, which is basically the step response because the input is a unit step. So let's see, since we have an LTI system, we will use the convolution sum, and here we are trying to express the convolution as summation of h of k times x of n minus k. This will give us this equation 0 if n is less than 0, and this summation of n is larger than or equal to 0, as we have seen on the whiteboard, which will give us 1 minus 3 over 4 to the power n plus 1 over 1 minus 3 over 4 if n is larger than or equal to 0, which is this kind of expression. And here we have the plot of h of k and x of k, and doing it graphically. This is h of k, this is x of k. First you start with x of k, then you mirror it, then you shift it such that this sample starts at n instead of starting at 0. Okay, another example, a discrete time system with input x of n and output y of n is described with the following equation. Y of n is 1 over 4 summation of x of n minus k going from 0 up to 3. First, find the impulse response, then find the output corresponding to this input. And again, this is a typical question in the exam. I will be giving you a system described by a similar equation. First, you need to find the impulse response, then you need to find the output corresponding to a certain input by doing the convolution sum, or in case of continuous time systems, the convolution integral, as we're going to see in the next lecture. Okay, so moving to our whiteboard over here, we have a system y of n which is described by the equation y of n equals 1 over 4 summation x of n minus k. First step, we need to find the impulse response. In order to find the impulse response, we will let x of n to be an impulse, delta of n, and then we will be able to compute the impulse response by simply replacing every x over here with an impulse, and this will make y of n to be h of n. So h of n is equal to 1 over 4 summation k going from 0 up to 3 delta of n minus k. If we try to plot this, it will be simply 4 impulses at instance 0, 1, 2 up to 3, and all will have the same weight, which is 1 over 4. This would be the impulse response of this system. Next, we will need to find the output corresponding to the input signal u of n minus u of n minus 10. So in order to find the output corresponding to this input, y of n minus u of n minus u of n minus 10, which is samples of the value of 1 going from 0 up to 9. Let's go to our whiteboard over here. So basically this is x of k. It's basically unit step u of k minus u of k minus 10. Subtracting these two, only the remaining samples will be from 0 up to 9. And h of k, as we have found it, it's basically samples of the weight of 1 over 4 from 0 to 3. Now we need to do the convolution. We will choose one signal to keep it as is, and the other signal we will mirror and shift. Of course, it looks like x of k is more difficult to move. H of k is simpler, is smaller, so I would choose to keep x of k as is, and h of k I will do the mirror and shift. So the first step is to do the mirror. So we'll have our samples going from 0 to minus 3. All will have this weight of 1 over 4. This is basically h of minus k. And then we will do the shift. And the shift will basically make this 0 to be n, and minus 3 will be n minus 3. And all will have the weight of 1 over 4. This is h of n minus k. And now we are ready to do the convolution summation. So now that we have x of k, and this is h of n minus k, now we can do the convolution sum. Consider the values if n is less than 0. What's going to happen in this case? If n is less than 0, then we will get 0 for the multiplication of x of k and h of n minus k. So the first step over here would be that y of n is equal to 0 if n is less than 0. If we move back over here, if n is larger than 0, but n minus 3 is less than 0, so the overlap between x of k and h of n minus k would be from 0 up to n. Again, if n is larger than 0, but n minus 3 is less than 0, the multiplication will be non-zero for the range of values from k going from 0 up to n. And in this case, I can write the following. So it will be summation over the variable k going from 0 up to n, and we'll be summing. If you go back over here, this has a value of 1, this has a value of 1 over 4, so we'll be summing 1 over 4 basically from 0 to n, and this will be true if n is larger than 0 and n minus 3 less than 0. Going back, over here, if we consider the case where n is larger than 0 but less than 9, and n minus 3 is also larger than 0 but less than 9. In this case, let me draw it over here. It will be something like this. The 4 samples of the impulse response will be confined within the range from 0 up to 9. In this case, the summation will be from n minus 3 up to n, because this will be our new n and this will be our new n minus 3. And in this case, I can write the following. It will be summation from k equals n minus 3 up to n, and I will be summing 1 over 4, and this will be true as long as n minus 3 is larger than 0 and n less than 9. Going back, the next case would be if n is larger than 9 and n minus 3 is less than 9. In this case, the overlap will be from n minus 3 up to 9. And now I can write the following. That y of n would be summation k going from n minus 3 up to 9 and of 1 over 4, and this will be true for n larger than 9 and n minus 3 less than 9. Going back, over here, the last case we're going to have is when n minus 3 is larger than 9. In this case, if n minus 3 is larger than 9, there would be no overlap, and the output would be 0. So I can write the following. I can write it as 0 for n minus 3 larger than 9. So as you can see over here, the signal y of n is defined over 5 intervals. N less than 0, and here n larger than 0 and n minus 3 less than 0, which is basically n less than 3. So n larger than 0 and less than 3. And over here it's n larger than 3 and less than 9, and the next interval is n larger than 9 and less than 12, and here n larger than 12. We have 5 different intervals, and we have found all of these intervals graphically using the procedure we have been doing so far, which is replacing xn with k, keeping one signal as is, in this case x of k, and then shifting, and then start with mirror of h of k, h of minus k, and then shifting it with n, and then starting to change the value of n, see the different values of n, and how the different values will give us different kind of summation and different intervals for the convolution summation. So going back over here, we have done this part, the impulse response, which was 1 over 4 summation over k from 0 to 3 delta of n minus k, which is basically 4 shifted impulses, all have the weight of 1 over 4, like this one. And this is the input signal. We have x of k impulses with the weight of 1 from 0 up to 9. I have chosen x of k to be as is, and h of k will be mirrored and then shifted. And now shifting this signal to the right and left and trying to get the different intervals as we have seen on the whiteboard. And these will be the 9 intervals we have found using the detailed analysis we did in the whiteboard, and this will be the final answer. Of course, if we try to plot it, it will be something like this. It's easy to plot. And in doing so, we have used this summation of a constant going from m to n is basically the constant c multiplied by n minus m plus 1. Let's go back over here and see. So summing 1 over 4 from 0 up to n. From 0 to n is n plus 1 samples. So 1 over 4 plus 1 over 4 plus 1 over 4, n plus 1 times is basically 1 over 4 times n plus 1. Which is this result. So basically, in this example, we have used this summation of a constant from m to n will be the constant times n minus m plus 1. And this will be it for today's lecture. In next lecture, we will continue with the convolution sum, and then we will move to the convolution integral.